Hello students, good morning and welcome to the class on information theory and coding. We have been discussing module 4's important concepts of error detection and error correction. We have been discussing the linear block codes. And in the last class we had seen what is meant by generator matrix, what is meant by parity matrix, what is meant by Hamming matrix, also called as parity check matrix. I hope you recall whatever was discussed in the last class. Let me write it this way, that at the source we have data vectors and we have code vectors. Code vectors are constructed using parity matrix. Okay, and using parity matrix there is one more matrix called generator matrix. Now using the generator matrix only all the code vectors were obtained. This was at the source side. Now at the destination side you have a received vector, and at the destination side you have a Hamming matrix, and at the destination side using the Hamming matrix you will compute a syndrome for the received vector, and using the syndrome we compute an error vector for the received vector. By means of the error vector we can correct the error that is present in the received vector. That way whatever was the C that we construct back at R, and whatever was the parity matrix, even the parity check matrix or Hamming matrix is obtained again by means of the parity matrix. And again this generator matrix is also obtained by means of the parity matrix itself. So this way I hope you recall all the basics that were discussed in the last class. Now always syndrome and error vectors are single row, even this received vector is single row, even the data vector is single row, even the code vector is single row. Whereas parity matrix, generator matrix and this Hamming matrix, they can be having multiple rows and multiple columns. Please recall all that. Now based on that I had discussed this note that the row in which the syndrome is present in the H transpose indicates the bit position in the received vector which is under error. In the example which we worked out, the error was in the 4th bit position, and hence that particular bit can be directly flipped for performing the correction. That is because we are using only the binary channel of communication, which means we are using only zeros and ones. So whenever we detect the error in a particular position, it is so easy to correct it just by flipping the bit there, 0 to 1 or 1 to 0. So with this brief recap, let me proceed. We had discussed the syndrome in the last class. Now how this syndrome can be implemented using a hardware, that let us see in today's class. In the previous class I had shown you the hardware counterpart of how we actually transmit the code vector or how we generate the code vector. Using the generator matrix we had an expression for each code vector which was in terms of the data vector. Same way at the receiver side how syndrome is calculated, let us see it now. So we know that R equals small r1, small r2 up to small rn. R is the received vector and S is the syndrome which will have S1, S2 up to Sn minus k. Now we also know that Sc is nothing but R into H transposed, where H is the parity check matrix or Hamming matrix. So we can write the equation for this S equals R into H transpose itself as S1, S2 till S minus K equals R1, R2 till Rn into, please recall the construction of the transpose of Hamming matrix. So here I have written the transpose of the Hamming matrix, where the identity matrix is coming down and that parity matrix is coming up. So this is the transpose of Hamming matrix. Now we can always write S1 equals R1 into P11 plus R2 into P21, and that way we go on. Please remember, in this particular course, we use modulo 2 addition for this error detection and correction. In the conventional matrix multiplication, it is always normal addition, whereas we are using a binary addition here. So I am putting this XOR symbol here. XOR is nothing but modulo 2 addition. So you will have to remember that. Otherwise, you may simply think it is a matrix multiplication only, so there must be a plus sign. Yes, it is a matrix multiplication only, but the addition is replaced with the modulo 2 addition or XOR operation itself. So that way, for S1 we can write an expression, for S2 we can write an expression, same way we can go on. S2 is R1 into P12 XORed with R2 into P22, that way it goes on till the end. And lastly, Sn minus k is R1 into P1 comma n minus k XORed with R2 into P2 n minus k, that way it goes on till the end. Okay. What is this last XORed with Rn? You can see that we have this identity matrix here. So you can see that it is always be, even with the S1, it is XORed with the last element is Rk plus 1. That is because we have the identity matrix there. In the identity matrix, you can see here in the row there is 1, next row there is 1, in the last row the last bit is 1. So actually we get XORed with Rn. So using these expressions, we can write the circuit now for the syndrome. Now the circuit can be implemented by means of switches, by means of memory elements, by means of registers at the receiver. Now at the top you will see the register only. The registers LSB is R1, registers MSB is Rn. Now R1 is obtained here. Actually all the received bits are stored in the register, and from the LSB or from R1 it is put into the parity bit P11, and then it is XORed with R2 into P21. It goes on that way, XORed with Rk into Pk1, it goes on that way, Rk plus 1 is coming here. Rk plus 1 corresponds to that 1 in the identity matrix row. Similarly, we can write for S2. S2 is R1 into P12 XORed with R2 into P22 XORed with Rk into Pk2, lastly XORed with Rk plus 2. Same way we can proceed. The last syndrome bit or the MSP of the syndrome vector is R1 into P1 comma n minus k XORed with R2 into P2 comma n minus k. Finally, Rk into Pk comma n minus k, the last one is Rn itself, that is XORed. So in this way, hardware for the syndrome calculation circuit can be implemented using a register and using these multipliers and using the XOR operation. So you can visualize the hardware that is required at the receiver. We need an n-bit register, and then we need so many multipliers. Each multiplier will have one input bit from the parity matrix and one input bit from the register. Then the multiplied output has to be connected to a XOR gate, and XOR gate is having so many inputs here. You can see here for S1 it is having inputs up to k plus 1. You can see that way. Actually with each syndrome bit, the number of XOR gates are increasing, so to say. Of course, I cannot say it is increasing because at the identity matrix there is only one particular row. So it is not increasing. The number of XOR gates are, number of inputs to the XOR gates are remaining the same. But you can visualize the XOR gate circuitry now, as we have studied in the VLSI course, and you can also visualize the XOR gates layout now, and you can visualize XOR gate is the most complicated logic gate out of all the other gates, and because of which always the hardware of XOR gate is time consuming and it is costly. Because of time consuming, because of multiple types of inputs there, XOR gate is the most expensive logic gate out of all the logic gates. Now any adder requires XOR gates, multiplier contains again adders, all adders require XOR gates, multiplier requires XOR gates. Here also we have XOR gates. As XOR gate is the most expensive logic gate, people are even today doing research on how to reduce the circuitry of the XOR gate. You can visualize the XOR gate circuit diagram. 2 input XOR gate will have AB bar plus A bar B, means it will have how many transistors? A into B bar plus A bar into B. So you will have 4 transistors at the bottom, 4 transistors at the top, totally 8 transistors. Along with that you need 2 more inverters for A bar and B bar. That way you will have 4 plus 4, 8 plus 2 plus 2. Totally 12 transistors are required for the implementation of one XOR gate. Now if at all we reduce the number of transistors there, we are saving the cost for the XOR gate. That is why even today in the VLSI domain, people are doing research on the hardware implementation of XOR gate using different logic styles or using different architectures. As my expertise is in VLSI domain, I thought let me share that point with you. So let us proceed with the ITC course now. This page, let me rotate it. I'll have to rotate it. How? Rotate view. Okay. Counterclockwise. Fine. We had seen the syndrome calculation circuit now. Now let us have an exercise using all these concepts. Consider a systematic 7,4 linear block code for which the parity matrix is given by P equals 111, 110, 101, 011. This is the parity matrix which is used at the transmitter. It is also used at the receiver. It's a systematic 7,4 code. Means what? Total number of bits in the code vector is 7 and the data bits are 4, which means the error bits are, the check bits are 3. So it is 7,4, n is 7 and k is 4 here. Now the exercise asks us to find all the possible code words. That means we have 4-bit data now, right, from 0000 till 1111. Now we have to find out all the possible code words for all the data vectors. Next part is a single bit error has occurred in each of the following code words. Means let us say we have CA, CB, CC, CD, like that we will have 16 code words. Now he says in RA, this is the received code word at the receiver and RB is the received code word. First one is 01111110 and RB is 1011100. This is the received code word. At the destination, we have to detect and correct the errors now. Now he also asks us to draw the encoding circuit and asks us to draw the syndrome computation circuit. Let us find the answer now. Now we can write the generator check matrix. The generator check matrix can be written as G equals what? You can see here, identity matrix along with the parity matrix. Please recall whatever I had discussed earlier. As we have 7-bit now the identity matrix has to be 4 cross 4. And the parity matrix is given as 3 cross 4. We always write this IK and P. Please remember that. G equals IK, and I had put a pipe symbol there. I had put a vertical line there. It is not actually, separation of two matrices. It is actually writing all these bits in a single matrix. That is why I had put a separator there. That pipe symbol or vertical line was a separator. So we have this IK is I4, is 4 cross 4. So you have to write an identity matrix here. As soon as they give, in the exercise when they give 7, 4, N is 7 and K is 4. So when you have to write G, you will have to visualize G equals IK and P, where IK is this K itself. We should have identity matrix of 4 cross 4. Then we are going to write the parity matrix. So here, this generator matrix is 4 cross 4, identity matrix is 4 cross 4, and the parity matrix is as it is we are writing here. That is anyhow 4 cross 3. 4 cross 4 and 4 cross 3. Naturally, it is 4 cross 7. So that is the generator matrix. Now what is that? C equals D into G. Data into generator matrix using the modulo to addition, not using the regular addition. So now for 0, 0, 0, 0, obviously code vector is all 0, 7 zeros. For 0, 0, 0, 1, no, for 0, 0, 0, 1, D into G. For the 0, 0, 0, 1, just find out. First one 0, second one 0, third one 0, fourth one 1. So when it is fourth one 1, you can see here the fourth row is coming here, 0, 0, 0, 1, 0, 1, 1. That itself is coming here. Let me admit the student. So you can see when there is this 1 bit here, anyhow all other three preceding 3 rows are going to be having 0 elements only, and we have 0, 0, 0, 1, 0, 1, 1. Next 0, 0, 1, 0, obviously you can see 0, 0, 1, 0, 1, 0, 1. 0, 0, 1, 0, 1, 0, 1. For that 0, 0, 1, 1, there is addition modulo to addition, and accordingly we get 0, 0, 1, 1, 1, 1, 0. You should always remember the first 4 bits of the code vector are same as the data vector that we had discussed earlier. Only thing is the next 3 bits are going to change as per this matrix multiplication with the modulo to addition. So I have written the matrix already as it is directly by computing all these things manually. But my suggestion or advice to you, in whatever way you take it, or instruction in whatever way you take it, is that you personally perform this exercise at home. Take a notebook and personally perform this exercise on your own. Otherwise, I am just showing you the complete table in the PDF because I have already written it. But I had done all these computations of C equals D into G before filling up the values in this table. So it is better that you do this on your own, only then you will understand. Okay. Next 0, 1, 0, 0 is again 0, 1, 0, 0 into 1, 1, 0. That particular row can be directly written here. Wherever in the data vector you have a single one, you can directly write that particular row. But wherever you have multiple ones, you have to perform the matrix multiplication using modulo to addition. So like that I have gone up to 1, 1, 1, 1. So last one is 1, 1, 1, 1. And I get the last 3 bits also as 1, 1, 1. So we have all the code words now for all the data vectors. Now this is the code word that is going to be transmitted from the channel encoder. For the corresponding data word, this is the code word that is going to be transmitted from the channel encoder. Okay. channel encoder is going to receive this data vector and it is going to perform this matrix multiplication of C equals D into G and it is going to transmit it. That can be one approach. Another approach is channel encoder can have a lookup table for each received data vector. It can simply look into the lookup table where already 16 code words are stored in the RAM or in the ROM or any particular memory, maybe flash memory itself. Now, in the lookup table, whatever is the particular code word stored, that can be directly transmitted serially from the channel encoder. All these implementation of channel encoder is up to the designers, up to the circuit designers. They are basically VLSI designers or let us say circuit designers only. Okay. So then we have found out all the 16 code words now. Now he has given us two received vectors RA and RB and he asks us to find out the error that is present in the received vector. Let us proceed now. Let me rotate this page again. Oh, it became ultam pulta. Okay, let me proceed now. Now the parity check matrix at the receiver is given by parity transposed into I3. That what is that I3? I3 is n minus k. Please recall all that. So we have to write the transpose of the parity matrix now. That is 1110, 1101, 1011 is the transpose of the parity matrix. Now we write I n minus k, that is 100, 010, 001. That is the Hamming matrix now. Now, how to find out the error? For RA, the given received vector is 0111110. We can find out the syndrome. We know that the expression for syndrome is R into H transposed. So we will write this RA and we will write the same transpose of this Hamming matrix. That is this. Again, I repeat, I am just showing you on the PDF page, but you will have to personally take pen and book and you will have to work out this exercise on your own. Otherwise, it is not so easy to understand these concepts. So, S equals R into H transposed. So, given is RA, SA equals RA into H transposed. So, we will write the transpose of this Hamming matrix. Now, let us perform our matrix multiplication with modulo to addition. We get here 0111110 into the very first column, we get the first bit as 1. Similarly, the second bit as 1, the third bit as 0, performing the matrix multiplication with the modulo to addition or XOR operation. Now, this 110 is the syndrome which we obtained. Where is it present? 110 is present in the second row. You can see here, the syndrome 110 is present in the second row of transpose of the Hamming matrix. That means, in the received vector, the second position is in error. So, the second bit in RA is in error. Therefore, the corrected RA is 0011110. The very second bit is flipped as 0. Now, for the second one, for RB equals 1011110. Sorry, 1011100. Let us calculate the syndrome. In the same procedure, syndrome is 101. Now, 101 is present in the third row. As this is the third row of H transpose, the third bit in RB is under error. Therefore, the corrected RB is third bit, let it be flipped, 1001100. So, now the error vectors also can be written. For the first one, it is the second bit which is under error. For the second one, it is the third bit which is in error. we can write EA and EB in this manner. And we can always calculate the code vector is received vector XORed with the error vector. But we have already visually verified it. Now my question to you students is that we have those 7 bits in the received vector. And there can be how many errors now? If at all we consider a single bit error, there can be errors in 7 positions, right? If there are errors in 7 positions, how many rows are there in the Hamming transposed? There are 7 rows in the Hamming transposed. What does it mean? For each position of the bit in the received vector, there is a particular row in the Hamming matrix. So now when you look at this H transposed, what do you understand? That you should get a syndrome of 111 if there is a error in the first bit. Syndrome of 110 if there is error in the second bit. Syndrome of 101 if there is error in the third bit. Same way, if at all the last bit or 7th bit is under error, you will get a syndrome of 001. That is fine. Now the question to my students who are listening and have understood this concept is, all the syndromes, are they predefined? Is the question. The syndromes, bit combinations, are they predefined? Is the question. Is it so? Let me elaborate my question. Now for the very first bit error, first position's bit error, you should get a syndrome of 111. So my question is, the syndrome 111, is it predefined? Because you can see 111, 110, 101, 011, 100, 010, 001. Is it predefined is my question. Any answers? Chandra Mohan said yes. Now how is it predefined? Kuldeep also said yes. Can you justify your answer as yes? How did you conclude that it is predefined? Any answer? Okay, the answer is by knowing the number of received bits. Yeah, number of received bits is 7 only here. That is fixed. Based on the number of bits of RA, we consider the syndrome. That is correct. We will have a code vector also 7 bits. We will have a received vector also 7 bits. That 7 bits are fixed. My question was not that. Based on the 7 bits only, we will have 7 rows in Hamming transposed. That is obvious. My question was, 111 is fixed as a syndrome for the first bit error. 110 is fixed as a syndrome for the second bit error. So this bit combination of 111, it is fixed. That was my question. Was it predefined? Was my question. This 111, 110, 101, 011, are they predefined was my question. Look at the parity matrix, you will get it. The answer is, we have this parity transpose. We have written the parity transpose. I cannot rotate this parity, you can see here 111, 110, 101, 011. See here 111, 101, 011, which means in this particular Hamming transpose matrix, you are getting the parity matrix itself along with the identity matrix. You are not going to get any other elements. That way it is predefined. Everything we are defining in terms of the parity matrix itself, right? At the receiver we have parity transpose. Again we will have H transpose, Hamming transpose. You have a parity transpose along with the identity element for Hamming matrix. Again for calculating syndrome we have Hamming transpose. So we will get the parity matrix back. We are getting this parity matrix back. Okay. When we are getting this parity matrix back, whatever are the elements in the parity matrix, they themselves are going to come in the H transpose also, along with the identity matrix elements. So that way syndromes are fixed. Now my next question is, our H transpose is 7 cross 3, 7 rows and 3 columns. Whereas the bits used are 3. So there can be 2 power 3, totally 8 combinations, right? Totally 8 combinations. Out of that 8 combinations, 7 combinations are present here. You can see 0, 0, 0 is not there. 0, 0, 1 is there. Then 0, 1, 0 is there. 0, 1, 1 is there. Then 1, 0, 0 is there. 1, 0, 1 is there. 1, 1, 0 is there. 1, 1, 1 is there. Only thing is 0, 0, 0 is not there. In the H transpose, 0, 0, 0 is not there. Which means we cannot get a syndrome of 0, 0, 0. Now my question is, why this 0, 0, 0 is missing in H transpose? That is my question now. Can anybody answer? I think my question is very clear. We are using a 3-bit vector for syndrome in the H transpose. Naturally, we should have 2 power 3 equals 8 combinations. Out of 8 combinations, in the H transpose, we have 7 combinations present. 0, 0, 0 is missing in the H transposed. So 0, 0, 0 cannot be a syndrome. Now my question is, why 0, 0, 0 is missing here? That is my question. Any answers? Okay, no answers. Fine. Okay, one answer is it depends on the order of the RB matrix. No, RB is a received vector. That is 1 cross 7, right? Single row and 7 elements. If all zeros indicate no syndrome is present. Yeah, what does it mean? It can't be 0 since it is an error. So syndrome is 0, 0, 0 cannot exist as such. That is my question. It can't be 0 since it is an error. But error can occur, error need not occur also, no? It is not necessary that error has to always occur. Error need not occur also. If a 7 bits are sent from the transmitter, all the 7 bits may not be having error at the receiver. Out of the 7 bits, there may not be any single error also. That possibility is also there. And if all are zeros, it indicates no syndrome is present. That is fine. My question is, in this H transposed 0, 0, 0 is not there. Can it be there? Can it not be there is the question. Right now it is not there. Can this 0, 0, 0 be there in the H transpose? Will we have any such H transpose where we will have 0, 0 is the question. Fine, you are all trying to answer. Let me clarify the answer. There cannot be 0, 0, 0 in H transposed. Okay. In H transposed, there cannot be 0, 0, 0. Why? Because what is H transposed? That is parity matrix along with identity matrix. In the identity matrix, always one element in the row will be 1. So there cannot be 0, 0, 0 in the identity matrix. Now there cannot be a 0, 0, 0 present in the parity matrix also. Can you tell me why? When we choose a parity matrix, the parity matrix cannot have 0, 0, 0 as one of its elements. Can you tell me why? My question is, in the parity matrix, there cannot be 0, 0, 0. That is why syndrome also we will never get a 0, 0, 0. So the answer that in the parity matrix there cannot be 0, 0, 0, because obviously if it is 0, 0, 0, we will get a code vector also 0, 0, 0, only 7 zeros. Then we can't get the complete code vector, correct? We don't get the complete code vector. If at all in the parity vector, we have on a particular row where there is 3 zeros, then we will be not be getting a correct code vector. Why? C equals D into G, right? That G equals IK and P, right? Remember that. So if in the parity matrix, if there is 0, 0, 0, then we will have erroneous behavior. We will not be getting correct code vectors. That is why in the parity matrix there cannot be 0, 0, 0 at all. Now, the challenge here you can see, the challenge is this H transpose is a unique transpose matrix. Means except for 0, 0, 0, all other binary combinations are present here. Right? 0, 0, 1 till 1, 1, 1, all the binary words are present here except for 0, 0, 0. 0, 0, 0 cannot be obviously present here. That means when we have a parity matrix, how did we decide upon this 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1? Just look at that. The choice of this parity matrix itself is again carefully to be done. You can see this. There is no identity element here. You can see there. Because we know that there is going to be an identity matrix later on. So 1, 0, 0 cannot be an element in the parity matrix. 0, 1, 0 cannot be an element in the parity matrix. 0, 0, 1 also cannot be an element in the parity matrix. That is how we have written the parity matrix in this manner only. So the choice of a parity matrix also is very important here. That is why I had this much of discussion now. We cannot arbitrarily write one parity matrix and we cannot arbitrarily proceed. If we write that way, there can be conflict in the syndromes. There can be the same syndrome in multiple rows. Then there can be conflict or there can be confusion, so to say. So the choice of a parity matrix also is as important as error detection and correction ability at the receiver. Because the choice of the parity matrix is happening at the transmitter. Now the same parity matrix is going to be utilized at the receiver. Normally when we go through this exercise, you may think that it is the receiver which is more complicated because the receiver has to do a lot of algorithmic approaches or computations. And we may simply think that transmitter is only going to do C equals D into G and it is going to send it. But the choice of the parity matrix at the transmitter is as important as the error detection and correction that is happening at the receiver. That is the point here. Otherwise, all syndromes have to be unique here, right? If the syndromes are not unique, what may happen? If the syndromes here are not unique, what may happen is, if I have two rows having the same bit combination in H transposed, how do we decide which row is having error, which position is having error? Based on the row of the H transpose, we are detecting the error. Now, if the syndrome is the same in two rows, there is erroneous behavior. That is why the final conclusion is the choice of the padded matrix is also important. It is not just a random arrangement of bits there. That is the point. Just to stress on that point, I had to discuss these things in detail. Let me proceed now. Now we have to write the hardware for encoding circuit and syndrome. So, from the generator matrix, we can observe that C5 is D1 XOR D2 XOR D3. Let me show you the generator matrix. I will have to rotate this page once again. Rotate view counterclockwise. You can see the generator matrix. In this generator matrix, we can come to a conclusion about C5, C6, C7. See, 1 1 1 0, 1 1 0 1, 1 0 1 1. Just look at this column. Now, this corresponds to C1, C2, C3, C4. The four columns in the generator matrix correspond to C1, C2, C3, C4 because they correspond to D1, D2, D3, D4. Right? It is nothing but D1, D2, D3, D4. It is unique that way. Now, how about C5? C5 is D1 across D2 across D3. And C6 is D1 XOR D2 XOR D4. And C7 is D1 XOR D3 XOR D4 because in the middle we have these zeros. Now, from the generator matrix, we can easily find out the equation for C5, C6 and C7. That is the point here. Now, let me proceed. Again, I will have to rotate clockwise. Okay. So, we have this C5 equals D1 XOR D2 XOR D3. Okay, it is very difficult for me to use my brain and my speech as a synchronized manner. D1 XOR D2 XOR D3, C6 is D1 XOR D2 XOR D4, C7 is D1 XOR D3 XOR D4 as per the generator matrix. Now, using that, we can write the encoding circuit. Now, you can see C1 is same as D1, C2 is same as D2, C3 is same as D3, C4 is same as D4. Now, C5 is, you can see, it is D1, D2, D3, all three are connected to an XOR gate. C6 is now again D2 and D1 is there and then D4 is there. C7 is now, here D3 is there and D4 is there and D1 is there. That way, you can write this XOR gate and make connections accordingly as per these equations, and the equations are obtained from the generator matrix itself, and using that you can write this circuit diagram. This will be asked in the tests also, this will be asked in the final exams also. In the next class, let me discuss about the syndrome circuit for this particular exercise. As it is time up now, I am ending the meeting now. See you in the next class.